All right, continuing on now with vectors. Now you will see one-dimensional vectors, but also you'll see two-dimensional vectors. And this is basically the same as what we had last semester in Physics 1. So if you got vectors then this shouldn't be a big issue. But I know that many of you sort of struggle with that. So let's just take a moment to review with vectors in 2 dimensions. So say I'm given a configuration of 3 forces like this, Q1, Q2, and Q3. And I just want to know what is the magnitude and direction of the force on Q3. So let's start just by labeling all the forces, given the free body diagram with all the forces that are acting on Q3 in this case. So here I have a positive charge, I have a negative charge here, and a positive charge here. Now the force on Q3 due to Q1 will be in that direction, so that's going to be F on 3 due to 1, and then the force on Q3 due to Q2 will be in this direction. I'll call that F3, 2. Now a couple of things I want to do here is I want to calculate the magnitude of F31 and F32, and then I also want to, I'll just go ahead and we'll do that part first. I want to draw my X and Y axes, which I'll do right here, and I want to determine what is this angle right here. Now F32, that is the force on particle 3 due to particle 2, is on the negative x-axis, but F31 is some angle above the positive x-axis. I want to figure out that angle so that I can go through that whole process of finding the x and y components of that force, that vector, and adding up the vectors and then finding the new magnitude and direction. So let's just start by finding this angle. I'll call it theta. That angle, if I draw a triangle on these charges, that angle is going to be the same as this angle. All right, so I'm going to redraw this triangle over here. I have a 3, 4, 5 triangle. Pardon me. That's not a triangle, that's a rectangle. This side is 4 meters, this side is 3 meters, and I want to know what is this angle, theta. So if you recall, the tan of theta is equal to opposite over adjacent. That's 3 over 4. And so theta is the inverse tan of 3 over 4. And I get 37 degrees. So that angle is 37 degrees. All right, now let's go ahead and find the magnitude of F31 and F32. This is just applying Coulomb's law. So I'll write out F32, all the numbers to start. F32 is equal to K. K is equal to 9 times 10 to the 9th. But then newtons meters squared per Coulomb squared. Let's see, F32, I'm concerned with Q3 and Q2. Now Q3 was 1 times 10 to the minus 9 coulombs, because it's 1 nanocoulomb, and nano is 10 to the minus 9. And Q2 is 2 times 10 to the minus 9 coulombs. Notice that I didn't include the sign, that even though Q2 is a negative charge, I do not include the sign because the sign I take into account when I say, well, these opposite charges are going to attract. And so that gives me a force in the negative x direction. And that's going to be divided by r squared, where r is 4 meters squared. Let's see, so these 10 to the 9ths cancel, so I get 9 times 2 is 18 times 10 to the 9th divided by 16. Let's see, 18. I get 1.1 times 10 to the minus 9 newtons. All right, so that's the magnitude of F32. Now, in a similar way, I can find the magnitude of F31, 9 times 10 to the 9th. That's my K value, 1 times 10 to the minus 9. That is my Q3, that's in coulombs. That's the charge of that third part of Q3. And then I want to know the charge here, so it's 3 times 10 to the minus 9 coulombs divided by the distance squared. Now this distance is 5 meters. You can find that in a couple of different ways. You can just recognize that this is a special triangle, a 3, 4, 5 triangle, or you can say that the hypotenuse, which I'll just call D here, is equal to the square root of 3 squared plus 4 squared, and that's equal to 5 meters. 9 plus 16 is 25. Root of that is 5. So divided by 5 meters squared. And this gives me the magnitude of F31. I get 1 point. So let me, I'm going to keep a few more sig figs here that I need to make them different. 1.08 times 10 to the minus 9 newtons. And then up here, this was actually 1.125. So let me revise that just a little bit. So you can see that the numbers are different. 1.125. Okay, so those are the magnitudes of those forces. I'm just going to redraw them on a vector diagram. Let's see, I think I have some more space on this next page. F32. So I had F32. This was 1.125 times 10 to the minus 9. And then I had F31, which was 1.08 times 10 to the minus 9 newtons. And this angle is 37 degrees. All right, so now it's just a two-vector problem. I want to resolve that first vector into its x and y components. So I will have, let's see, I'll do this in purple. I'll have a y component here, and then I'll have an x component here. All right, so I'll just call this, sorry, let me go with, that was F31y, the y component of F31, and this is going to be the x component of F31. Okay, so I can calculate that. F31, the y component, is equal to F31 times the sine of theta, which is 37 degrees in this case. I get 6.5 times 10 to the minus 10 newtons. That is going to be in the positive direction. And then F31x is going to equal F31 cosine of 37. Remember, this is how we find our x and y components. When our angle is measured off the x-axis, the x component is the magnitude of the vector times the cosine of the angle, and the y component is the magnitude of the vector times the sine of the angle. If you need help with this, you need to come see me, because we're going to see this. You won't see problems that are as long and drawn out as this, but you'll certainly see bits and pieces of this problem on the exam coming up, and you'll have extra practice in the homework as well. All right, so this is equal to 1.08 times 10 to the minus 9 times the cosine of 37. And I get 8.625, it's called 8.6, which is 10 to the minus 10 newtons. All right, so those are our components now. So now if I redraw my vectors, it'll look like this. And now instead of having two vectors, I have three vectors. 1.125 times 10 to the minus 9. I have a vector in this direction. That was my y component, 6.5 times 10 to the minus 10 newtons. And then my x component is 8.6 times 10 to the minus 10. Okay, so those are my three vectors, and now I want to find the sum of those vectors. So I'm going to draw my coordinate system again. There's only one vector in the y direction, so I'm going to keep that 6.5 times 10 to the minus 10 newtons. And then I want to treat these two vectors right here. So I have one in the positive direction and one in the negative direction. Just to find the magnitude of or to find the new vector that you get when you add up those two vectors, I just take the difference in them. I say 8.6 times 10 to the minus 10 minus 1.125 times 10 to the minus 9. I get negative 2.65 times 10 to the minus 10 newtons. And so that vector, since it comes out negative, is over here. 2.65 10 newtons. All right, so now those are my two vectors, and they make up a new vector, and I want to know what is the magnitude and direction. I'm going to draw a little triangle here. I'm going to have my first vector will be in this direction. It has a magnitude of 2.65 times 10 to the minus 10 newtons. And then my other vector, which was the y component, is 6.5 times 10 to the minus 10. And then the vector that I'm really concerned about is this vector. I want to know this angle, I'll call it phi, and I want to know what is the magnitude of that. All right, that's simple trigonometry. I can find my force. It's the square root of the sum of the squares, so 6.5 I get 7.0 times 10 to the minus 10. Newtons, that's my magnitude. And then I want to find my angle, phi, which is going to be the inverse tan of the opposite over adjacent. That is 6.5 times 10 to the minus 10 divided by 2.65. Those cancel out. So 6.5 inverse tan, 68 degrees. We have to be more clear though, because that's 68 degrees above the negative x-axis. So that's our answer. We have a force of 7.0 times 10 to the minus 10 degrees at 68 degrees above the negative x-axis. Listen, folks, vectors come up a lot in the study of all sorts of physical systems, because whenever we have quantities that have direction, they're often, well, you have to use vectors to describe them. And a lot of quantities have directions attached to them. Velocities of objects moving, bodies of water, velocities of things in your body as they move, the forces that act on various objects. These are all vector quantities, and so you need to have a basic understanding of how to do vectors. Now, you won't have problems that are this drawn out, like you won't have a single problem that would require this much time, but you should certainly know how to do this, how to find the components of vectors, how to find the magnitude, direction of vectors, how to add two vectors. Those things will be assessed on the exam coming up, gosh, probably a week or two or so. All right. You'll also see some conceptual questions like this, just asking you to, not guess, but estimate what the vector is, pick the correct vector. I'll let you do this on your own. Here's another example of a test question, which you can try on your own and do on the online quiz. And we will pause there and pick up with the electric field.